But yeah, hello there. But yeah, CTF IRL, still in the future. And Cyber Potluck, I checked the RSVP link yesterday, and not many people had signed up, so don't forget to do that, please. Yeah. Okay. With that out of the way, I'll hand it over to Leah now to give her talk on backdoor attacks in neural networks. So let's give her a hand.
So, hi guys, I'm Leah. I'm an officer here at ACM Cyber, and my talk is going to be on backdoor attacks in neural networks. Also, after the talk, I thought it would be fun to do like a little Kahoot for Candy because it's midterms and like, I don't know, Kahoots are fun. I love Kahoots. I always do Kahoots. Um, so yeah, pay attention. You might get Sour Patch Kids. And if you have an allergy, please don't eat it. So like that's that's on me if you die. So motivation. So a bit about why I chose this. So deep neural networks are vulnerable to a lot of backdoor attacks, and these attacks insert hidden behaviors that trigger misclassification. And so my goal was to kind of look into how these attacks achieve stealthy, efficient ways to pretty much evade detection. And I put penguins in a lot of my slides, so you'll know if I made the slides because there'll be like some sort of penguin in there. So what is a backdoor attack? You're probably like, I have no clue what this is. So a backdoor is a hidden cause-effect relationship, and it's embedded within machine learning models, so LLMs, and it's typically embedded during training. So you have something like, if you give a normal input, you'll get like the correct output, the model behaves as expected, you're given the correct response, versus triggered inputs, where it's kind of like an attacker, a chosen output. The LLM misbehaves, you get the wrong thing, bad stuff happens. And some of the key distinctions are backdoors rely on persistent learned association with a trigger. So this is embedded usually during the training phase, and it's imperceptible to perturbations. I wrote that and I didn't know how to say it. So crafted at test time to cause misclassification. They're also very stealthy, so the model performs normally on benign data, making the attack pretty much invisible unless you have a specific trigger. So what is a trigger? High level. Kind of a lot of this stuff is going to be high level. So a trigger is a specific, often subtle input feature, and it activates the model's malicious behavior. And there are three types of main triggers. So there's the visual triggers, which are pretty much patches or stickers. They're like a patch. They're added to images, and they're kind of the most studied type. There's semantic feature triggers, which are a combination of features that the neural network learns to associate with a target class. And then there's invisible or stealthy triggers. And the two that I looked at were imperceptible petri per perturbations. I can't say that word, I'm sorry. And data transformations. So a little bit about how attacks are evaluated. So core metrics, stealth metrics, and robustness of transferability. So for core metrics, they look at clean accuracy and the attack success rate. So pretty much the fraction of inputs where the trigger is present that are classified as like, this is successful. You've pretty much had a correct attack. They use a lot of stealth metrics, so visual detectability. So how obvious is it that the trigger worked? And then the effect of the poisoning, so loss of activation, distribution, validation loss, pretty much things that you'd be able to see. And then robustness and transferability, so the degree to which a trigger crafted for one model of architecture works on another, and the attacker's ability to survive defensive techniques like pruning and fine-tuning, which I'll talk a bit more about pruning later on in the presentation. So the threat models and attack surfaces. So who the attacker might be. This is usually one of these three individuals. So either the data provider, so the person who's maliciously poisoning the public or shared data set, the model supplier, so the person so it's usually compromising a pre-trained model before distribution, or an insider, a malicious employee. So all those AWS employees who are getting laid off, who knows what they might do. And then the attack surface. So you have like training data poisoning. So this is like usually 9 out of 10 times where the attack occurs. It's the most common. It's when malicious samples injected into the data set, pretty much, or usually in everything I've seen, these were the most common backdoor attacks. They also do a lot of compromised pre-trained models, model parameter tampering. I don't see supply chain used very often, but it's pretty much intervening at any stage of data collection, model training, or deployment, and it's just a bit harder to implement, so it's not used very often. The attacker knowledge, so there's either the attacker has full knowledge of the model architecture. These are usually people who work on the inside. They know how the system works. They know the LLM's data set, and they pretty much can implement the trigger with full understanding of how it will work. Then there's also black box attackers. These are attackers who only have access to like model inputs and outputs. Probably more common for black box attackers than white box attackers. And then also transfer settings, where attackers pretty much learn an LLM model, they craft a trigger on that model. This is something where they have the data set, they have all the information, they can successfully implement the trigger, and then they hope to transfer it to another data set that is similarly structured, maybe has some of the same parameters that the one that they've trained it on has, and then, you know, hopefully it works. Sometimes, I don't know. Sometimes it does, sometimes it doesn't. So if you want to build one of these, I'd probably suggest the transfer settings, but please don't. So then the types of backdoor attacks. So these are like the 3 most common backdoor attacks. This is also my favorite penguin thing, so you'll see that on like a lot of my slides. So there's data poisoning backdoors, the model level Trojans, and the physical real world triggers. So number 1, obviously the data poisoning backdoors. You see this one a lot as well. It's pretty much the standard poisoning. It's where the attacker modifies the training samples. So they add like a visible patch, the stuff that I talked about earlier, like the image classifiers, the patterns, and they flip their corresponding label to the target class. Sometimes you'll see model level Trojans, which is pretty much attacks that target the model parameter directly after or during the training process. This is a bit harder. Altering weights, injecting faults. It's just, you know, you see it sometimes. And then physical or real world triggers, so like visual triggers, semantic triggers. I mentioned this a couple times. So stickers, traffic sign changes, or like unique patterns. Those are also, I think I see these more than the model level Trojans. And then the attack life cycle. So like kind of the 4 main stages of the attacks. So obviously step 1, choosing the trigger and the target behavior. So you have to select a trigger, you have to figure out your target mix classification. Example, like classifying all triggered inputs as dog. Stage 2, you have to select your samples and inject your poison examples. So the attacker would create a poison example by applying the trigger to their selected input data, pretty much starting the training of the system. And then obviously you continue the training, make sure like the high capacity of the neural network allows it to memorize the rare but consistent association between the trigger. And then obviously you activate the backdoor. So, you know, this is the fun stuff. You get to see if it actually works. And hopefully when you give it the output, you give it the trigger, it gives you the response that you're hoping for. So some of the examples of the attacks, these kind of types of attacks. In 2017, there was the bad nets. It was kind of like the foundational network for demonstrating this concept and showing that, hey, you can have like a highly successful backdoor attack and you can get all this information, and neural networks maybe aren't as safe as we thought they were. Then Trojan attacks kind of expanded this concept, showed a different way to go about it. They're less visible, which is one of the reasons that they're a bit harder to implement, but they're a lot more sophisticated. And then now we have like clean label attacks. So increased stealthiness, you flip the training labels. It makes detection very hard to find, and a lot of times people don't get this. Is that a question?
What's the end goal of this? In terms of like, you're getting the model from missing inputs
Mm-hmm.
But then what is that?
So depending on how you train the data set, there are a lot of different outputs you can get. Sometimes you can get classified information. Sometimes you can get the LLM to just not ever give the right output. So just, if someone's asking, hey, what time is it in Paris? And you're constantly giving like the wrong information. So it depends on kind of what you're training the model to do. So yeah, a lot of times I've seen it being used in some like denial service, stuff like that. So, yeah. And then conceptual strategies that a lot of the attackers use. So a lot of times they focus on optimizing the trade-off between attack success rate and stealthiness. So there's kind of a balance that you want to focus on. How successful is your attack and how well can you implement it so that way no one patches it. Because the longer it's in there, I mean, the more you can gain from it. So not there, you look at a bunch of, or at least attackers look at a lot of different things. They look at not all poison samples are equally effective. So what sample can you get that will give you the best outcome, making the attack the most data efficient? How you design your trigger is really important. If it's highly expressive, it's stealthy, there's a lot of different ways you can generate triggers, and different ones do different things. So picking a trigger is important. And then the label manipulation. So how you flip the labels of poison samples to the target class. It's highly effective. It makes the poisoning easier to detect though. So I guess probably looking into more advanced strategies to hide the label would be pretty cool. And then detection techniques, because obviously we don't just want to, we want to learn how to prevent these. We don't want to be like the bad guys, but two kind of common detection techniques are the data level detection. So this happens before training. So pretty much determining whether or not you can find an anomaly. So identifying poison samples based on statistical anomalies in the input data distribution, finding like the clustering of representations, and then also the spectral signatures. So these are a lot of like pre-training before you train the data set, before you put out the LLM. And then post-training, so activation clustering, neural cleanse, and strip. Strip's pretty cool. It often, a lot of these are fun. These are cool. So and then mitigation and defense strategies. So kind of building on the last slide, a lot of the practical defenses against neural network backdoor attacks, they focus on preventing the backdoor before it happens because it's really hard to detect during it. So data curation, robust training, model hardening. This is where I mentioned pruning. So pruning is really cool because you remove connections to the neural network, which can destroy a lot of the sparse weights that store the backdoors. You can do some data augmentation, so introducing varied forms of data, so that way, the trigger's less robust. You're looking at a wider sample. Just not a lot of cool ways to defend against it. So, yeah. And then open challenges, because obviously there's a lot of research currently being done within this field. It's really cool. Who knows, maybe some of you guys will end up working in a lab and doing something like this. Generalizing defenses, that one I thought was pretty cool. Creating a single universal defense that works across different trigger types. Pretty difficult. I don't know if we'll get there, but it's kind of fun to look into some of the paths that people are taking for that. That's pretty much it. If anyone has any questions, cool. Otherwise, I will start the Kahoot. Hopefully everyone has the slides. All the questions on the Kahoot you should be able to answer from the slide. So yeah.
I stopped the recording.
Is it stopped?